All right, so welcome everyone to our seminar. I'm pleased to introduce Chris Leonardi from the University of Queensland. Thank you very much, Chris, for making yourself available for this anagram webinar. And Chris is background in computational mechanics. He has been working with DEM, lattice Boltzmann coupling a lot, also working on high performance computing. So I'm very interested to see what you can um, tell us about that. And your talk today is going to be on migration, segregation, percolation, and clogging, recent learning from high fidelity simulations of particle transport. So, Chris, I now hand over to you. Thank you again for making yourself available. And we might take questions at the end, unless you prefer to have them in between. But I leave that up to you, Chris, how you want to run it.
Thanks, Klaus. Thanks for the introduction. Thank you, everyone, for taking an hour out of your day to listen to me talk. I think I will take questions at the end just so I can manage my timing for how long it takes me to get through the presentation. And before I start, I'll acknowledge my team, past and present, Lukash, Travis, Nathan, Dimitro, and Lachlan, who have all contributed to various aspects of this research. So today, if I can get my pointer working, I will talk about the high fidelity suspension transport modeling that we do here in the School of Mechanical and Mining Engineering at UQ. And it will be presented with a focus on applications related to oil and gas production, specifically gas production from unconventional reservoirs, and in particular, particle transport in pores and fractures. And so I'll speak briefly about the modeling technology that we use, and then summarize some applications related to proppant transport, and then focus a bit more on some work that we did for an industry partner on the performance of a low quality sand, and then finish off with some thoughts on upscaling transport and flow. I've got some supplementary slides on uh, relative permeability analysis in rough fractures, but I don't think I'll have time for those today. And I've also got, if anyone's interested in some of the multi-physics aspects of our modeling work, I've got some additional slides on that as well. So the context for the research that I do is coal seam gas production, primarily here in Queensland. I came to UQ in 2013 from MIT in the US, where I was actively involved in the research work of the MIT Energy Initiative and doing modeling work related to shale gas production. And so I came to Australia with the view of transferring that research to the local industry. And in general, what do we deal with when we're dealing with production of methane from coal seams is complex flow of at least two phases, so water and gas, in the presence of some fines, in a very complex fracture network characterized by face and butt cleats. And if we are looking to stimulate production from a coal seam, we will induce that by hydraulic fracturing, where high pressure fluid is pumped into the reservoir to generate a fracture, which is then supported by some suspended particles, i.e. the proppant. So the flow physics is incredibly complex, both prior to production and then once production starts. And the regime changes dramatically. We go from situations of pure water flow through to commingled water and gas flow to predominantly gas flow as well. And these things happen in, as I said, not just a primary induced fracture, but a range of cleats that interact with that fracture. And we use high fidelity modeling to try and answer some key research questions that relate to this problem. And I should hopefully have this animation playing. There's a little laggy at the front, but what we see here is just a rendering of one of our analyses where we've got particles suspended in a primary fracture. You might be able to tell that this is a shear thinning fluid. And this fracture interacts with some branching cleats, which cause leak off of the fluid and also the formation of particle occlusions due to size exclusion at these fractures here. We can't see the fluid. We've hidden it so that you can actually see what the particles are doing. But the types of questions we ask of models like this are, how do these particles self-organize when they are polydisperse? What drives clogging and screen out of our proppant particles? What's the retained permeability of our fracture after we have stopped pumping fluid? How do particles leak off into the cleats? What's the optimal carrier fluid rheology? And as I mentioned earlier, how might a low quality proppant perform in this type of application? As you can see in my figure caption there, we do this work using coupled lattice Boltzmann discrete element modeling. And I'll only very briefly describe that here because I don't think these things are new to anyone that's on this Zoom meeting. But we use the LBM because it's very effective and efficient at porous media flows where the geometry is very complex and also where we would like to couple our flow to a large number of moving obstacles like discrete elements. And as we were discussing just prior to the start of my presentation, the LVM is no longer a research code. It's widely distributed with commercial CFD solvers. And although it's very good for porous media flows, it's probably more prominently used in vehicle aerodynamics, and some large companies have bought effectively research LBM codes to do aerodynamics of cars and trucks in a commercial setting. And then, of course, we use the discrete element method for the particle mechanics. Over here there's a fun fact. On the right-hand side is an analysis of a two-leg transfer chute at Dalrymple Bay Coal Terminal up in Queensland. And this is work I did as an engineer prior to commencing my academic journey back in 2004, 2005. And I remember presenting work like this at the International Conference on Bulk Materials Handling that is held in Australia, and being one of maybe the only people presenting bulk materials handling work using discrete elements. And these days, I haven't been to that conference series in a long time, but I do know that the work is somewhat dominated by computational analysis now, which is nice to see, but certainly not something that I'd take credit for. The coupling is fully resolved. And so what that means is our approach looks like something on the right. We have many more LBM grid nodes per particle diameter than we would in an unresolved situation like you see on the left. And so what that means is the analysis is very expensive. So for that introductory video that I showed you, we would be talking of hundreds of millions of lattice Boltzmann grid points, even though the particle count is on the order of 5 to 10,000. And the memory requirement on GPUs is also substantial. So tens of gigabytes, and some of the really big analyses are approaching 100 gigabytes. And so this is to be contrasted with, say, a CFD DEM approach using finite volume, where the particles sit as a mass fraction within a finite volume cell, and the momentum equations are coupled accordingly. We have implemented a bunch of multi-physics extensions. You can see an animation there showing large eddy simulation for turbulence. We also, using a similar approach, can model a range of non-Newtonian fluids, so power law, shear thinning, shear thickening, viscoplastic, and now more recently viscoelastic fluids. We have a student doing some nice work on that. Temperature effects in both the fluid and the particles, electromagnetic forces, electrostatic forces, and most importantly, for certain flow regimes, Reynolds lubrication for contacting bodies. And in particular, an implementation of Reynolds lubrication that acknowledges the fact that the Reynolds lubrication force is never truly singular for particles that have some roughness that's relevant to their length scale. And so the force, as these particles get close together, asymptotes to some value, although there is definitely an additional finite repulsive force there. It's not infinite as the gap between particles approaches zero. And that's a very convenient physical reality that makes the modeling just that bit easier. So the work or the tools we use are open source. So the stuff I show you today has been done using lights, which is coupled into our LBM code. We have previously coupled in ESIS particle, which is a DEM code from UQ. And my collaborator Lukasz from Poland has also coupled in another DEM code from France. I think it might be Yade from memory. But if you are interested in how this works, you can download the source, you can compile, and you can run some tutorials, and you can play with the stuff that we've been developing, and you can also read about the implementation in these two key papers that are summarized here. So in terms of applications, the first one I want to talk to is about the transverse migration of polydispersed particles in a channel. And so from a calcium gas perspective, what that means or what that was motivated by was this idea that microparticles could be injected with the hydraulic fracturing operation to enter branching cleats and stimulate them. So have these very small particles enter the branching cleat network and remain in place once the fluid flow has stopped to keep those cleats open when the well is producing gas. And one of the key challenges to this idea is that size control on that type of particle is very poor. So if you are looking to buy a few cubic meters of micron scale particles, you are not going to get a very tight size control on the product that you purchase unless you pay a prohibitively high cost. And so for a particle that has a median size of, say, 20 to 50 microns, you will have a range of anywhere from a few micron up to about 100 micron of diameter in terms of the product that you get. And so we were interested on how this product might flow in a fracture and how it might enter the branching cleats that you can see schematically here next to this primary fracture. And we were inspired to some degree by some experiments that were done in the US back in the 90s that showed some really interesting behavior. So occlusion formation at these cleats or otherwise cleats that admit but then fill with these small particles as well. So how do we do this from a computational modeling point of view? Well, we set up a periodic cell that looks like this, which has two no-slip walls and two periodic pairs of boundaries. So what flows out of this domain flows back in the rear, and same for the top and the bottom. And we then measure the reorganization of this polydispersed suspension over time. The time scales here can be very long. So in this particular problem, the length scale is not so much the issue, but what more so is the issue is the number of explicit time steps that are required for things to equilibrate. And there's two things that need to equilibrate here. There is the bulk migration of this set of particles inside the fracture, and then there is size segregation, and they happen at different time scales, and the latter happens at a much longer time scale than the former. In the middle here, we show a couple of representative distributions, polydispersed distributions of particles. And so you can see that the radii range from about 1 to 4 microns. See, these are all 1 to 10 micron in diameter, 2 to 10, I should say. And we validate the modeling approach against some well-known experimental data, looking at the variation in solid volume fraction and the flow profile that emerges when bulk migration of this suspension has equilibrated. Well, a couple of things that we were able to show with this work were first and foremost, if one measures the bulk and species dispersion coefficients, which are defined here, you can show some similarities between polydispersed suspensions and bidispersed suspensions. So it was previously known that from the statistics of a distribution, so the mean, standard deviation, and the skewness, you can infer some things about a suspension. So you can make some inferences about its maximum packing ratio, for example. But what we were also able to show is that with those statistics, you can make some inferences about the migration of the suspension, the bulk migration, I should say. So this dispersion coefficient C is a measure of how close things are to the center of the channel. So if C is 0, all of the particles in your suspension are sitting on the center plane. If it's 0.5, all the particles are sitting at the walls. And so it varies somewhere between that. And in these graphs on the bottom, you see the results, the dispersion results for 5 different distributions. But on the left, these are polydisperse, and on the right, they are bidisperse. They have the same statistics. So we have pairwise similarity between a polydisperse and a bidisperse suspension. So that means to say they have the same mean standard deviation and skewness. And so what you see is the same trend in terms of the way they migrate within the channel, and also very similar magnitudes for the pairwise similar suspensions. And so that tells us something very useful about polydisperse suspensions and how their behavior is the same as bidisperse suspensions. And that's very valuable when you would like to complement your modeling with some experiments, because trying to do these types of migration experiments with a polydisperse suspension is difficult when it comes time to classifying what you see at various places within the channel. With a bidisperse suspension, it's much easier to use some image processing to classify whether a particle you see is the small one or the big one. If it's polydisperse and there's an infinite, well, a semi-infinite set of diameter, then it's much more difficult to classify which diameter particle you're seeing where. And so these links that we were able to show with the modeling are very useful. But I think even more interesting than that was the data that showed the emergence of this reverse migration, where small particles accumulate at the center of a channel under certain conditions, under what is known as reverse migration. And so what we found was when the solid volume fraction is above zero 0.3, even not even as high as 0.4, and the flow conditions are right, we start to see the formation of this plug of small particles, and this plug will actually start to over-consolidate at the center of the channel. This is not what we expected. We hadn't seen these types of results in the literature before, and it's actually the exact opposite of what we were trying to achieve, which was to have these small particles migrate to the walls and then find their way into the branching cleats and then deeper into the reservoir. Why this happens, as far as I know, is not yet fully described, but we are kind of aligned with this theory that had been previously proposed, that the higher shear fluctuations of these smaller particles, particularly at the boundary of the plug, drives a certain number of them into the plug with time. And so small particles fluctuating at the edge of the plug eventually enter the plug and continue to feed that system. To try and break down this behavior, we started exploring the idea of flow reversal and partial flow reversal, which has to some degree been studied in the literature, but only to a limited extent. And when it comes to partial reversal, that is to say, like some mean flow component with an oscillating component, there is very little that's been done, I guess, rigorously. And so we've got some data here for different periods of oscillation on the left, where there's no mean flow component, so things just oscillating backwards and forwards around a fixed point. And we can show that at very large, long wavelengths, or long periods of oscillation, that's these X's here, the behavior converges on what you would see in unidirectional flow. But as the frequency of the oscillation gets higher, or the period gets shorter, we actually start to see, as evidenced by the change in the bulk dispersion coefficient, a reversal of that migration. So if the amplitude of the frequency of oscillation is right, we can switch from conventional to reverse migration and vice versa. What we're also able to then show is that when we add a mean component, and for anything to get from A to B, there has to be a mean component of the flow. Otherwise, oscillating around a fixed point is of limited utility. And so what we found is that for rather small mean flow velocities, we could actually get particles to migrate away from the plug in the center and further towards the channel wall. But the time scale for this to happen is pretty long. And as you can see, the mean flow velocity is also very, very low as well. So um, it's improbable that one would continuously pump with an oscillation and a mean flow in order to get this kind of behavior. There would need to be some hybrid unidirectional and oscillation required to get the effect that we were after. So I'll move on from the transverse migration work and talk a little bit about clogging and screen out because, as you can imagine, in narrow fractures with particles of finite size, the potential for local clogs to form, which then nucleate into large jamming or what's called in the industry screen out events, is a real risk. And so in the industry, there's a bunch of kind of like rules of thumb, like W on D equals 2.5 as being the ratio of channel width to particle diameter at which screen out will occur in a fracture. But I guess that kind of empirical number is not well, I guess not that universal, particularly when you have fractures that vary in aperture locally and at longer length scales as well. What also happens when you're dealing with small particles on the order of a few micron is that depending on the chemistry of the fluids that they're flowing in, there can be some electrostatic forces at play, which influence the way particles interact with their walls and with each other. And so what we did was we built this little test cell of a synthetic rough fracture and we flowed it with particles at varying solid volume fraction to generate statistics of the probability of a clog forming. And so these plots that you see here the probability of a clog as a function of solid volume fraction um, as calculated using many, many repeats of these simulations. And so going from the left graph to the right, we've taken the number of trials from 10 to 40, and in doing so, really narrowed the confidence interval on these predictions such that we have, very tight description of what these probabilities are. We can pick off a couple of numbers from this logistic curve. So phi 90, phi 5 and phi 95. So phi 5 is the solid volume fraction when you have a 5% probability of clog forming. And phi 95 is the solid volume fraction when you have a 95% probability of a clog forming. And so we pick those numbers off from a bunch of different tests of varying parameters, and then we plot them on some maps that look like this. And so the first one, so we're plotting here phi 5, the bottom line with the squares, and we're plotting phi 95, the upper line with the circles, for here a range of W on D numbers. And so the first thing that we notice is that you can form clogs above W on D of 2.5, and we saw that here up in these numbers here. What we also saw is that when you start with a very narrow fracture where it's only a little bit wider than the particles that you're transporting, and you get wider, the probability of clogging actually gets more likely. The solid volume fraction required for clogs to form drops quite significantly, and that's because of the mechanics of particle interaction. So just below W on D of 2, you have the ability for two particles to almost but not quite travel parallel to each other down the channel. And so when that happens, they interact with each other in the walls and they form a local clog. And as you get wider again, we get this region around just over 2 where we saw no evidence of clogs ever forming. But then as you get wider again, you have the ability for 3 particle clogs to form. And so that's why we see these data here emerging. You can also see rather intuitively that as you increase the friction, which we tune for these models based on some other data, as you increase that friction, you increase the probability of clogging or you reduce the solid volume fraction required for clogging to occur. What we could also test was the influence of DLVO forces on clogging in these types of scenarios. And so we were able to define some non-dimensional adhesion numbers between particles and themselves and particles and the walls, and then look at how each of those affects clogging behavior. And if we look at the graph on the right, we see that the wall adhesion, so the influence between the interaction between particles and the walls, particularly attractive, of course, quite quickly diminishes the ability for any meaningful solid volume fraction to travel through this fraction. So we go from 10% down to only a couple of percent as we increase that electrostatic interaction and reduce the ability for particles to be transported through that fracture. What we also showed is that the particle-particle attraction was secondary to this particle wall attraction. And I mean, at least in terms of the particle wall attraction, it is somewhat intuitive that particles bonded to the walls effectively narrow the channel and then increase the likelihood of a stable clog to form between two or three particles, and then grow from there. Just very quickly, I'll show you some data on the influence of carrier fluid rheology on occlusion formation. And so here we have another little test cell where some particles are flowing past a branching fracture. The three contours, six contours on the left are using a Newtonian carrier fluid, and on the right, they're using a shear thinning power law fluid for various combinations of particle size and cleat width. So here, 100 mesh refers to particles that are about 150 micron in diameter. And you can scale the other particle sizes from these mesh numbers as well. I'm terrible at these old imperial units, but I do always remember that 100 mesh is 150 micron in diameter. And so you see as the cleat is much bigger than the particles, you get particles leak off, and eventually they screen out in those branching cleats. And so what happens when you have a non-Newtonian fluid, and particularly a shear thinning fluid in the same scenario, is that the occlusion formation is totally different. And so the shear thinning behavior actually suppresses these occlusion formations quite well. And so what happens is that as you have some particles either screen out within a cleat or at the T intersection of a cleat, you locally reduce the fluid velocity in that region. And if you do that for a power shear thinning fluid, you locally increase the fluid viscosity and thereby reduce the likelihood of fluid to flow into that cleat. So you get a feedback mechanism there, which forms a type of plug in that cleat, even though it's not full of particles. And so when you do that, you then promote flow within the primary channel past that branch, and it continues on its merry way. And so we very clearly demonstrate some ideas that people in industry have about how these kinds of occlusions can be controlled, because if they are left to grow like you see over here, there's a likelihood, and as you saw in those experimental photos earlier on, there's a likelihood that those occlusions can become, similar order to the width of the fracture and a major obstruction to further particle transport. Okay, so the last thing I want to focus on is this work here, which was to analyze the performance of what I'll call a low quality sand. And what I mean by that is a product that doesn't meet the API definitions of what a proppant should be like. And it doesn't meet those definitions for a couple of reasons. It's very angular. Its crush resistance might be a little bit poorer than what you would expect for an API standard sand. But being a non-API product, it's a lot cheaper. And so if you are trying to source sand in southern Queensland, you have a limited number of API product suppliers, and they're not local, so they have to be transported from elsewhere in the country or have to be shipped in internationally. And so the idea for this work was to use a sand facility from southern central Queensland and the product that they provided, which looks like this photo here. Yes, very angular, very poor size control, and crush resistance a little bit mixed as well. So we're interested in two things. So how this product flows in the types of fractures it'll encounter, and then what it will do after it's been placed inside inside a fracture. And so we try to parameterize this as best as we can, given that the wide degree of uncertainty with all these things. And so the first thing we do is we parameterize the fracture generation using a power law model of the fracture roughness, and then also incorporate the surface correlation and the aperture. And so basically what we do is we generate our fractures as these from this mathematical model. We can inform the mathematical model from the statistics of some imaging. So we did some digital optical microscopy to determine what the roughness spectrum is of some coal samples. And then we use that power to then inform this model, which then allows us to generate as many realizations of rough fractures as we like you can see over here on the right-hand side. This one here has a mean width of 0.5 millimeter. It has a mean roughness of 20 micron, and the surfaces are perfectly correlated. Over here, you see some more examples of the fractures we generate, and on the right, you see one where the fractures are not perfectly correlated, so C is 0.8. At 0.8, the decorrelation is not, it's tricky to see by the naked eye, but it is there. And as you go below 0.8, it becomes more and more obvious that the surfaces are not perfectly correlated. In reality, these surfaces can decorrelate for any number of reasons because of shear dislocation under lithostatic stresses, or because of mineral growth over time within these cleats, or any number of other reasons. The next thing we needed to do was try and parameterize our particle angularity. On the left-hand side, this is Lachlan's attempt at rendering or creating these sand particles based on their true statistics. To model with particles like this would be very expensive. You can see there's a many number of facets describing each particle, and the contact resolution and detection for that would be very expensive. And so what we decided to do was build some canonical particles that were 1D, 2D, and 3D out of clumps of rigid spheres. And we described their shape based on the ratio of the longest length, A, along a side, and the radius of the particle that makes up the clumps. Once we have some fractures and some particles, we can flow them, and they look like this. So you can see the zero-dimensional spheres, 1D clumps, 2D clumps, 3D clumps. And if you spend some time watching these different videos, you see local holdups occurring, particularly for the 3D and the 2D particles as they interact with the walls and other particles in the pack. But that obviously is of limited use from a quantitative point of view. So what we did with these data is we generated these graphs of flux versus volume fraction. And so on the y-axis, we have the flux in the fracture that's been normalized by the cubic law for Poiseuille flow in between two parallel plates. And on the x-axis, we have the volume fraction up to, of course, a number of about 0.6, where we would expect absolutely nothing to be moving beyond that point. Our data from the simulations are the black lines with the solid black symbols. We also plot here some reference information from the literature and from the industry. So the first one, this dashed line here, is the what you would expect from a Krieger-Doherty suspension viscosity, defined like this, where the viscosity varies as a function of phi m, and phi m is your maximum flowing solid volume fraction. We also have on here the dotted line, the Kozny-Kármán law for effectively flow through packed bed. And on this graph, we also have this red line, which is a screen out criterion from the oil and gas literature. And what it shows is that this, under these conditions, we would expect flow of this suspension to effectively stop at a solid volume fraction of about 12%. at which point it would drop down to flow through a packed bed. And so the flux, which is non-zero here, but it's a bit hard to see, would just be of the fluid flowing through a screened out bed of particles. So what we see from the data is that all of these things work at some point in the volume fraction range, but not universally everywhere. So the screen out criterion is pretty good in the low solid volume fraction region, but we see that particles are transported well beyond the point at which this model says that they should stop, that they should fully jam and screen out in the fracture. So the decay in permeability is continuous. We don't see a strong discontinuity like we see in this screen out criterion. And that's true for all of the analyses that we have run of this type. We also see that the Krieger-Doherty suspension viscosity works pretty well until we get up to about 20% solid volume fraction, after which we start to deviate. And we deviate quite a bit as the aspect ratio of the particles changes. So at an A on R of 0, these are spheres, we have curves that look like this, so reasonably close. And then as those 1D particles get longer, A on R of 1 and of 2, we deviate more and more. And as we deviate from the suspension transport model, we get closer to the flow through a packed bed model, which is the Kozny-Kármán relationship that we see down here. The one thing that's really interesting is that, one of the things that's really interesting is that as we widen the fracture, so we go from W on D of 2.1 to 2.5 to 3, and here it's important to point out where D is the equivalent sphere diameter for these clumps. It's not the diameter of the subparticle within the clump. It's the equivalent sphere diameter, which we could transport across all our different clump types. So as we widen the fracture, this influence of angularity disappears very quickly. And so you see that because all of these curves collapse on each other. They still deviate from the empirical laws that we've got plotted here at different points, but the angularity or the degree of angularity becomes insignificant once we widen the fracture. And it doesn't have to be very wide for that angularity influence to disappear. And we see the same sort of behavior when we go to the 2D triangular clumps and also to the 3D clumps. With the 2D triangular clumps, we have this kind of strange non-monotonic behavior where the A on R particles of 1, so these are smaller triangles than the A on R of 2, actually perform worse. And our theory there is that as those triangles get like larger planes, they more tend to align with the flow streamlines and therefore are less likely to screen out or jam within the fracture. For the 3D particles, we see in the narrow fracture that it doesn't take long or it doesn't take many particles for us to jam this system. And so here for A on R of 2, we're tracking the Kozny-Kármán law pretty well after about 15% solid volume fraction. So these most angular tetrahedral clumps slow up quite soon in the solid volume fraction range. But just like all the others, the influence of particle angularity disappears as the fracture gets wider. And as I said, it doesn't have to get very wide for it to disappear. But in summary, what we can say from these types of results is that the ability to flow these angular particles through a rough fracture is probably pretty good. We would expect the primary fracture to be more than wide enough for the angularity to not matter. And so whether it was a sphere, and some of the API sands are quite spherical, or whether it's one of these nasty angular looking things, they'll transport quite well. Beyond that, what we did was then look at how packs of these particles would behave once you started to flow water and gas through them. And so imagine your primary fracture packed with these non-API sand particles. or packed with a Wisconsin sand, which is an API product, or just packed with some spheres. And then you had fluids flowing through them, and those fluids could transport some smaller particles, some fines that could have been produced from the coal or from the adjacent sandstones, or some very small particles that were injected during the hydraulic fracturing process and are now looking to flow back. And so we're interested in how these things either screen out or percolate through these packs of particles. What we did is, well, first we analyzed the pore space that's generated from these different packs. And so what you see is that for our non-API sand, which have a wide size range and are very angular, our pore size distribution is pretty broad. Okay, so we've got plenty of pores that are down in kind of like the 10 micron radius range, and then plenty that are up around 120. So there's quite a wide variation in the pore sizes. And you can see that contrast when you look at the Wisconsin sand, which is more tightly clustered around the mean. And then for spheres, it's even more clustered around the mean, which you would expect because it is a spherical pack. So you've got, for this non-IPA sand, you've got some small pore throats and you've got some big pore throats, and they exist distributed throughout the pack. So what we did in terms of modeling is that we created packs of these three different particles, and then we flowed 100 mesh product through them in suspension. So 150 micron particles flowed through these packs, and then we measured where these particles would end up in these packs. So if you imagine this graph from left to right represents the pack, we could measure the percent of deposited particles as we increase the depth into the pack. We were able to check that our model is making sense by comparing the data for spherical and even Wisconsin particles, which are near spherical, to some data from the literature. That's this blue line here. And then what we could see is for our non-API sand, we were trapping a lot more particles in the pack than you would do if your pack was of spheres or of Wisconsin sand. And you see that in terms of the average breakthrough rate. So a much larger proportion of the particles entering the pack, but then getting trapped in the pack. And then going beyond that, you could see what that means in terms of the pressure drop in that pack. If you're excluding more particles within, first of all, admitting more particles into the pack because there are some large pores, and then screening them out because there are some small pores, you start to see a degradation in the head loss. And so if you look at the stars here, that's the pressure drop or the head loss for our pack of non-API sand, we see about a 26% greater relative head loss in this pack than you would do for spheres or for or Wisconsin sand. And so from an operational point of view, that's potentially problematic because you have a situation where you will admit lots of fine particles into your conductive fracture and then screen them out. And over time, you will degrade the conductivity of that pack, which is not good from a productivity point of view. And so with that, I'm finished, and I'll just say a little bit about what we're working on now, and that's trying to upscale the detailed information that we get from these models into things that are on the full fracture length scale. And so on the left are some results where we're looking to take the kind of flux volume fraction graphs that I showed earlier and map those to a fluid solver that allows us to actually capture not only the transport of particles, but also the arresting of those particles where the conditions are favorable for that. So this is effectively upscaled particle transport in a slot where some stuff's flowing in from the top left and out by the top right and accumulating on the bottom, as you can see with the growing red contour. But then on the right, some work that I started while I was on sabbatical last year at EPFL in Switzerland with Brice Lecampion and his group, who published PyFrac, which is a simple hydraulic fracture solver, which allows for the dynamic evolution of fracture width. Because in all of the work that I've shown today, the fracture width remains static. It doesn't change because of an increase in pressure or a change in the prevailing stress conditions. And so that's something that we feel is important for really understanding what's happening at fracture tips in terms of screen out as well. So with that, I think I've spoken for 43 minutes, which is a bit longer than I hoped. I have left some time for questions, and I would be happy to take any that you have.
Thank you so much, Chris. Very interesting talk and very nice animations you showed there. Colleagues, I would be happy to open up for questions. Are there any questions from the audience? I guess if you have a question, just
Hi,
unmute
Close.
yourself.
I
Yeah,
can
Aman.
start. Taking the
Yeah,
start.
go ahead, Aman.
Yeah. So, hi, Christopher. First of all, I just say hi. Sorry, I joined a bit late, so I didn't get a chance to to say hi. I'm Arman from UNSW. Also, hi to all the rest of you, Itai.
I think you just froze there, Aman.
Yeah, we've lost him.
Everyone. Yeah. So, so, can you hear me okay?
You
It's been cutting in and out, but I can hear you now.
All right. So let me see which. All right. So hopefully it stays connected. So yeah, my question is on multi-phase modeling. Which is, I understand it is, you have done some work on it. I kind of dabbled into it, kind of modeling flow of water and air in an unsaturated porous media. And my observation was that it is numerical stability is just like most cases I encountered numerical stability. I think it was mainly because of the difference between density of air and water, and there was like I couldn't get good results out of it. Let's put it this. Not that I worked a lot. I kind of dabbled into it, but I thought I'd just pick your brain on that. What do you think? What is your experience on that?
I didn't talk about that today, but I have some slides on exactly this. And so we do this, we're using a phase field LBM formulation, where we take those rough fractures that I showed earlier, and we solve for gas and liquid transport in these fractures. And so the contour here is showing the local fracture width, so it varies, and then the hatched region is the liquid and the water. The air is unhatched. So these have density ratio of about 1,000 and viscosity ratio of about 100. And it's pretty robust.
Sorry,
But
what
it's
is the
obviously
degree of
very,
saturation, Christopher?
sorry.
What is the degree of saturation?
So we map out the saturation entirely, and I'll just cut to some results that show you what that looks like.
Because my experience was that at low and high, especially I remember at low degree of saturation, I couldn't get anything out of it. It was
No, so I'll show you. There's a whole bunch here on initialization, but this is the kind of stuff that we can generate, where we not only create kind of REL-perm curves, but we quantify the uncertainty at which they exist for a certain fracture statistics. And so we generate 30 to 50 different analysis results for each saturation point on this REL-perm curve. And from the results of each of those runs, we can define a mean, a standard deviation, confidence intervals, etc., and then see regions where stuff just will not flow, where one phase is trapped, or where the other phase is trapped, or where they're co-flowing, where you have viscous coupling, where you have X-curve behavior, where you have pi curve behavior. So we find once you deal with the tricky boundary conditions, that it's quite robust.
all right. All right. And I imagine you can do similar particle tracking within this unsaturated modeling as well. Would that be?
Well, to some degree, but the challenge which we have not yet addressed is what happens when particles want to traverse the phase field boundary, right? Because we're using an immersed boundary type approach where the particles have some ghost fluid behind them. And so if that particle traverses from a liquid to a gas region, there's a challenge related to how you deal with that immersed fluid or that ghost fluid. And we haven't quite dealt with that yet.
All right. Yeah, interesting. Thank you.
No worries. I'll get back to the main presentation here.
Thank you. We have Marsha, if you want to ask your question.
Yeah, thank you, Christopher, for your talk. I have a quick question, maybe a bit basic. You talked about the interaction between particle and particle and particle and wall. I was a bit confused that how you quantify this interaction between wall and particle. For example, if you looked at the stress field in there or force or it was a slide 19.
Yeah. So there's
Thank you.
two things going on there. So the first one is that we still use and solve a standard soft contact model for the discrete element method. So a penalty-based method that says that for some given overlap, there's a repulsive force, which will drive a particle away from another particle or away from a wall. And of course, you need to set up your DEM solver such that that overlap is never too large and that your contact velocities are never too large as well. But then we have these forces, which are calculated from DLVO theory for electrostatic interactions. And so here we've just non-dimensionalized them by some other relevant parameters in the problem. And so these are just measures of the electrostatic attraction or repulsion of some of particles and other particles or particles and walls. And so this exists on top of the mechanical and hydrodynamic forces that emerge between particles as they interact with one another and with the walls.
Thank you.
No worries.
Hi.
Hi, Christopher. Great work. Really nice to learn about your work. Very nice. My understanding, correct me if I'm wrong, is that you're dealing with particles that are very small in this relative to, I guess, like, what is it, like 100 micron and below, I imagine. I'm just wondering how things would scale up if we think about fractures in geoscience sort of applications where particles starts to be big and the role of gravity, I imagine, starts to play a role, and then the direction of the fracture relative to the vector of gravity, I imagine, starts to come into place. I'm just like trying to wrap my head about that.
Yep.
Maybe you've looked into it.
Yes. So in terms of the fracture orientation relative to gravity, that's a very relevant one because in these subsurface problems, we can have fractures that occur on bedding planes. So where if you've got sedimentary basin like we have, and you have bedding planes between different materials, if a fracture emerges there, the transport in a horizontal well, the first thing is that the nature of that horizontal fracture is very different to something that's vertical, that has been formed by mechanical stress or by coalification. But you're right, the influence of gravity in those two situations is different. And it's one that we are hoping to quantify with some of our industry partners here. At a larger scale, we have talked in the past to some people that we're interested in, so large boulders in like faulting structures in the earth. One challenge that we do have is density ratio. So this immersed boundary formulation, as I said, carries ghost fluid behind the particles. And so for density matched scenarios, we can have some funny behavior emerge. So we rely on a particle density that's greater than the liquid density. And so I'm not sure if you were thinking of rocks in kind of like magma type situations, what the relative densities would be there, but I imagine they're quite similar.
No, I was actually thinking when the particle density and the fluid density are different, right?
Yeah.
So if they're very small, I guess the physics will be dominated by such forces that you show on this slide. But once they start growing up, the gravity starts to be significant and overtake it, I guess. So I was just interested in that sense. But it's very interesting as well, the density matched situation, I guess. But that's, didn't think about that. I was just thinking in terms of real fractures where there is permeability problem, just like what you described in geosciences, they usually could be very large fractures
Yes,
in
absolutely.
geosciences. Yeah.
Yeah. That's right. That's right. Yep.
And the particle, the pieces, the fragments are very big, I
Yep.
guess.
Yeah, for sure.
Thank you. Any other questions? Otherwise, I might throw one in, Chris. At the beginning, you mentioned that with the DM part, you started with ACIS particles. Now, I know Dion very well as well.
Yep.
But you mentioned that now you're using lights, and you also used Yates, so I'm associated with Yates. So it's just kind of like to understand why you sort of went into lights, and what the benefits are in this case.
ESIS particle, my perception of it as an outsider on the development was that it's very well set up for discrete element problems where you're interested in fragmentation of a granular medium, whereas lights was more set up for the transport of granular media. And one of the big advantages that we had with lights was the ability to import and map an STL of a boundary geometry. So these fractures that we import are STLs, which are generated with some scripts, and we could import those. We can resolve the contact between particles and each of those triangular facets very well. I'll double check that it was Yade, because now you've caught me out. I think it was, because Yade comes from Grenoble, right?
Yeah.
Yeah, I think it was, but hopefully it's one of those French DEM codes. So I think it's Yade. In terms of going forward, lights is no longer supported. Christoph Kloss and his team have their own commercial code called
Yes.
Asperix, which they focus their effort on. And so the community for lights is shrinking. And I am quite interested now in a community which is growing, which is granular materials in lamps. And so there is a guy in the US that's leading some fairly significant development there on solution of granular media problems using lamps. And if you search it up, you'll see a lot of really nice examples. What I'm unsure of yet is whether there are STL geometries native to the solver yet. But I think once there is, we will probably make the shift.
Yeah. Okay. And lamps is pretty much the underlying engine of lights. So
that's right. Yeah. I mean, it's all the same kernel, right?
yeah. Yeah. All right. Thank you so much. Any final questions, comments? Well, if not, we might close it here. So thank you so much again, Chris, for your very interesting talk, and welcome to the community. And yeah, we'll hopefully be able to interact with you more in the future.
Yeah, thank you again for coming along. Thanks for the invitation. It's been and thanks for the questions. It was a good discussion. I hope to see you all soon.
Excellent. Thanks, everyone.
Thanks.
Have a nice
Yeah,
afternoon.
everyone. Thanks
Thank
to
you,
us.
everyone.